Hello all and welcome back. So in this video, let us move forward and now let's see how can we determine if the given binary tree is a BST or not. Okay, so let's get started. Now let's first take an example. Let's say this is one example where we have these values. Now is this particular tree, okay, with these values, is it a BST? Well, it seems so because 50, 30 is less, 90 is more, 30, 10, 40, and 90, 80, and 100, right? So this seems to be a BST and it actually is. The most uh, people, like the mistake which most people do in this question is that they just check if your node value, okay, it should be greater than node dot left and it should be less than node dot right. So that's what actually the major people do the mistake, that they just check with this particular value and say that if it's a BST or not. The problem arises, let's say, if I make this as 60. Is this a BST now? It is not. But the check which we did in the last overall approach, that is going to fail because, sorry, that is going to pass because 30, yes, 50 is bigger. For 30, it is smaller, it is bigger than 10, but smaller than 60, right? So we just don't need to check with overall the left or the right node. I want to check in the entire subtree, which is the maximum value and which is the minimum value. Okay. So the very first thing which we have seen now is first check with minimum value of left subtree and maximum value of right subtree. Now if we do the same overall check, the same you will see is not going to pass because the maximum, sorry, the minimum, my bad, the maximum on the left side. Okay, so it's maximum. Okay, I think I made a mistake. 1 second. Yeah, so it's maximum on the left side. Okay, and minimum on the right side. Now when I find the overall maximum, it will come out to be 60, and this will say that hey, you are not smaller than me, so seems like I'm not a binary tree, right? Is there any other check which we need to do? I guess there is one more. So let me just explain you my example. Let's say now this is somewhere 20, okay, and this particular becomes 25. Now when you will get the maximum of this left subtree, it is going to be 25, okay, which is smaller than 50. Minimum of this is 80, which is greater than 50, and you are going to say it is. But the problem is it is not, because this particular subtree is not a BST. Okay, so the third condition in the initial video when I taught you about this particular BST concept, we made sure that each and every subtree also a BST, right? Also a BST. So these are the major checks which we need to perform. Okay, not just the one which we did just by checking the left value or the right value, so that we can say that our tree is a BST or not. Okay, great. So let us try to now work on this, everyone. Let us try to code this out. These are the conditions we have seen by different examples. And one thing more I would expect, that whenever now you are trying to reach to a particular problem, always think of different examples or test cases to validate your assumptions. Okay, great. So let us code this, everyone. Now here is the check BST file which I have created. In this, let me zoom it out. Yeah. In this, what we have to do, def check BST. I will be getting a root and I just have to tell if it's a BST or not. Okay. Base case, I think if root is none, I can say that it's true, right? It's a BST. An empty tree is actually a BST because it is like for all the conditions which we talked about, they are passing. So an empty tree is a BST. Let me write it down as well. Base condition. Empty tree is a BST. Okay, great. So now let us move forward and see what exactly we want. Now I want left max. Okay, so let's say we will make some function find max. Okay, something like this we are going to create find max, which we which will get me the overall max of the left subtree. Then I can get right min. Let's say it's going to get me the overall minimum of the right subpart. Okay, right subtree. This is what we talked about. This is the left subtree and this is the right subtree. I want the maximum value of left and minimum value of right. So if I'm able to get that, then I can be sure that okay, if I just compare that, I can be say that root with respect to root it's a BST, and then I can ask my children to just confirm if it is or not. Okay, so let's make another call, which is if no sorry my bad left BST. Okay, so left BST is going to be check for BST in root dot left, and right BST check BST in root dot right. Okay, great. Now what will be my answer? My answer is going to be something like this: left BST and right BST both should be true. Along with that, the condition which should hold is left max should be less than my root dot value, root dot data, and root dot data should be less than right min. Okay, so I will just repeat what are the four conditions. Left and right subtree, it should be individually a BST. That's the first thing. Along with that, left max, okay, the one on my left subtree, the max should be less than the root data, and root data should be smaller than the minimum on the right side. Okay, if all of this are checked, then I can say that I can return the answer. Okay, everyone. So I hope the idea is clear. Now to make it run, we will have to write these functions. So let us complete them. Great. So very first one is find max, where I will be getting a node. Okay. So the base case first, if node is none. Okay, let us talk a little bit about this. I think previously we might have done it somewhere in any question, but I still want to talk on this particular thing. What is the max value for a empty tree? If I'm asking that, hey, what's the max value if there is nothing in the tree? I think we should return. So there's a float of minus infinity. I say that minus infinity is the maximum value. The lowest number I know, I just say that, hey, it is the maximum value for an empty tree. Why is that? Because tomorrow, if there is any value which you take, right, it's going to be bigger than empty tree. And which is the smallest value I know? The smallest value I know is negative infinity. Okay, so this is how it is mentioned and written. Float of negative infinity. Okay, great. Then what can I do? I can do left max. I can find the find max of node dot left, and I can do right max. So I find the node of right. Similar question I think we have done in binary tree where we were required to find the min and the max. So once I have this value, once I have the left max, okay, so for example, let's say for this tree, I will find the max from here. I will find the max from here. Along with my value, I'm going to just compare all of them and return if it is return the maximum, right? So let us do this. Answer here is going to be max, the inbuilt function which we have, left max, right max, and the third option is node dot data. Okay, once I have this, I can return answer. Great. So Find max is done. Now let us do it the same thing for find min. Okay, let us see this. Great. So find min. Similarly, the way an empty tree had a negative infinity as the maximum value, the minimum value for an empty tree is going to be infinity. Okay, because any value which you take, let's say if it is even 1 million for the time being, okay, if it's a single node, let's say a single node tree with 1 million, then that's its minimum value. So to compare it to anything, okay, I should make sure that I'm comparing it to the biggest value possible. And thus we are taking it as plus or positive infinity. Okay. Once this is done, what I have to do? Min, min, same code, just I'm this time finding the min instead of max. Okay. And here as well, I have to find the min. Great. So it's now going to return me the minimum. Okay, everyone. So I hope the overall idea is clear. Now to check this out, what we can do, let's say we get root 1. Okay, let us just get some trees. So here, what can I do? Predefined trees. Okay. So root 1, root 2, root 3 equals predefined trees. So these are all binary BSTs. I know that. Let us check them still. Check BST, root 1. Let us print them out. Okay. So print this. Let us work on this. Yeah. Okay. So it is giving an error. Where is the error? Left. Okay. We missed out something. So binary tree node object has no attribute left. Where have we made this error? Line 14. So yeah, this is the error. Okay. Let us correct this. Have I missed it anywhere else as well? Yeah. So we copied the code. So the error will also get copied. And now it's saying that it's true, that it's a overall BST. Okay. For root 2, it's a BST. For root 3, it's a BST. Let us make one root 4. It's going to be binary. Have I have this? Yeah, BST node. So let me just make quickly a tree which is not a BST. BST node. And let's say 5 here. Then root 4 not left equals BST node of 10. So I'm adding 10 in the left side, and root 4 dot right equals BST node. Say I'm adding 15 on the right side. Should be fine. So let me just help you visualize this tree which we have created. It's having 5 in the root. Left is 10. Right is 15. Okay. So not making it a lot more in depth. The logic we know we have discussed, and that should be fine. So great. Let us just check this quickly. Print check BST root 4. Okay, print check BST, and it's giving false. Okay, so it's gonna work. We have discussed the logic and made sure that all the cases have been taken care of. So it's going to get you the overall answer if a given tree is a BST or not. The logic also seems to be a pretty simple logic. We have discussed all the edge cases. We have taken for the subtrees, finding the max, finding the min, everything we have done, right? But I think there is still a issue. Okay. And for that issue, what you have to do, you have to find the time complexity of this particular check BST code. Okay. So you're going to calculate the check BST code time complexity. I think we are doing some repetitive work here, which can be corrected. So let us see that if we can do that or not, if there is some repetitive work or not. And we will discuss that in the next video. But for the time being, I want all of you to check once that what is the time complexity of this check BST function. Okay. So cool, everyone. Let's meet in the next video where we will see if there is some way we can make it a little better. Thank you.